For my model, I wanted to explore grid and mesh systems. I created a square grid and diagonal grid, also known as a diagrid. The square grid was strong across the horizontal axis. When I applied stress straight along the y-axis of a vertical structural member, the resistance was good. However, slight movement and the whole panel slid across itself, creating a shearing effect which would eventually collapse. I moved on to a diagonal grid system. I measured and spaced each of the components so that the load would be distributed evenly across the whole structure. In my initial test of the load, it appeared that the diagrid was stronger than the square grid. From learning about vectors and the directions of loads and resistance, the grid is given its strength by distributing the load impact across many structural members, rather than relying on the cross-sectional width of one or two members. In the square grid, there is less directions that the resistance forces can travel, so when the load is applied directly along an axis, the resistance is quite strong. But there are no other pathways for the force kilonewtons to travel, so the impact can still be applied to the structure, but defection by bending, compression, and breaking is likely to occur. With the diagonal system, tension and compression forces work simultaneously along the many structural members and disperse the impact forces. The impact is met with the resistance force of many structural members. My structure takes the form of a bridge and could be a solution for green spaces or sporting fields, to be raised from the ground, such as between existing buildings. While the dead load of the structure remains constant, the live loads can be dispersed evenly across the horizontal plane, suiting the grid's behavior and performance. I incorporated this grid system to all structural elements of the model to observe the strength and stability of all axes. I added diagonal bracing to the vertical columns for 3 dimensions of support and beneath the horizontal surface so that the failure of the structure wouldn't immediately be from this component overbending. When I added weight to the middle of the bridge bends downward, pulling the columns inwards at the top and bowing outwards in the middle. All 3 members are experiencing bending moments and flexural defects. The stability is maintained by the corner bracing underneath and at the base of the columns, where the compression forces are travelled downward to the ground. The stiffness and strength of the grid and the material is enough to withstand this. However, in real life, this would not be an acceptable amount of movement, and the structure would be extremely uncomfortable for people. A single point load has a high influence on the stability of the structure, and although the grid seems to be able to respond well to axial stress and strain, the woven pattern of the grid would make it susceptible to twisting and torsion, which would be catastrophic as the whole structure would likely collapse.